In this video, we're going to talk about how to calculate average atomic mass. So first of all, for an individual atom, the atomic mass is the sum of the protons and the neutrons. We know that protons have a mass of 1 AMU. Neutrons have a mass of 1 AMU. So in an individual atom, the protons plus the neutrons add up to the atomic mass, which is a whole number. But when we look on the periodic table, right, we see that almost none of our atomic masses here are whole numbers. They're all some sort of decimal value. And that's because what's reflected on the periodic table is not an individual atom's atomic mass, it's an average atomic mass. It's the atomic mass of all the various isotopes of that element. So on the periodic table, A, the atomic mass, is a decimal because it's the average of those isotopes. Remember that an isotope is an atom that has the same number of protons but different numbers of neutrons. And because of that, they have a little bit different chemical characteristics. They're going to behave differently. When I look at the periodic table, I can tell which isotope is most abundant based on what my average atomic mass is closest to, because the isotope that is most abundant has the greatest impact on that average atomic mass. For example, when I look at carbon, I can tell that the most abundant isotope of carbon is 12 because this average mass is really, really close to 12. Same thing with nitrogen. I can tell that the most abundant atomic mass is 14 because the average on the periodic table is close to 14. Okay? So the formula to figure this out, to figure out what the average atomic mass is, takes a look at what the mass of each individual isotope is, as well as how abundant it is, how much of it is present in nature, how much of all the carbon is carbon-12, how much of all the carbon is carbon-14. So it takes into account the abundance. So our formula is the mass of the individual isotope times the percent of that isotope divided by 100. So we're basically taking the decimal and dividing by 100, or I'm sorry, taking the percent, dividing by 100 to get a decimal, plus the next isotope, its mass times its percent divided by 100, plus the next isotope, and so on and so forth. We would continue adding for however many isotopes we have. If we have 5, we would do this 5 times and add them up. If we only had 2, we would do it twice and add them up. So we're going to go through 4 examples of how to calculate this, just to illustrate several different methods, and then you'll be able to complete the activity that you have for homework, as well as use this process on our Beanium lab. All right, so for our first example, magnesium has 3 isotopes: magnesium 24, magnesium 25, and magnesium 26. You've also been given the percentages of each of those isotopes, and we're asked to find the average atomic mass. Now, in this particular problem, we're just given the whole number of the mass. You may, in further problems, be given an actual mass, and if you have the actual mass, you're always going to want to use the actual mass because it's a more precise value. But in this case, because this is what we're given, the masses are 24, 25, and 26 respectively. Our percentages 78.70, 10.03, and 11.27. From this percentage, I can tell that magnesium 24 is my most abundant isotope. And if I look at the periodic table, I can see that the average mass that our periodic table lists is 24.31, which agrees with the fact that this is the most abundant because this number is very close to 24. It's a little bit above 24 because our other 2 isotopes have a mass that's greater, so it skews that average up, but still very close to 24. All right. One thing I can do to help make my input in my calculator easier is divide my percentages by 100 before I plug them in. The easiest way to do that is just to move my decimal 2 places to the left. So I'm going to go ahead and do that here in my little makeshift data table. So 1, 2, 1, 2, 1, 2. All right. So here is my calculation. I'm going to take the mass, which is 24, times the percentage, 0.7870, plus 25 times its percentage, 0.1003, plus the mass, 26, times its percentage, 0.1127. When I put this in my calculator, I'm going to input it exactly how I have it written here with the parentheses, because that should make, try to move my calculator out of the glare. That might be as good as it gets. That way there's no confusion for my calculator about how I want it to interpret these numbers. So that comes out to be 24.3257. Now, for the purposes of your assignment, the directions on your assignment state that you are going to put this to 2 decimal places. When we do our Beanium lab, that will change just slightly because you are going to be doing some actual measuring in class. And so that would affect your sig figs. But for the purposes of these examples, we're going to go with the same direction that's on the homework, which is 2 decimal places. So 1, 2, that 5 is going to round. 24.33 would be our average atomic mass. Okay. For my second example here, same process, a little bit different data. This time I have actual masses, so I would use those more precise values. I have 3 isotopes of oxygen, oxygen 16, oxygen 17, and oxygen 18. Their actual masses, and I have 2 of my 3 abundances. Because of the data here given, it's showing that I only have 3, so the total of my 3 isotopes abundance should be 100. So if I take 100, I subtract away these 2 here, that's going to give me my missing percentage. So 100 minus 0.04 minus 0.20, and that's going to come out to be 99.76. So 99.76 is my missing abundance. Once I have that missing abundance, I can go forth and calculate that average atomic mass. I'm going to do it the same way I did in the previous question. I'm going to move my decimal places first and then plug into my equation. So 1, 2, 1, 2. I'm going to have to backfill a 0 here. 1, 2. I'm going to have to backfill a 0 there as well. Okay. So average atomic mass. So I'm going to take my actual mass, 15.9949 times 0.9976 plus 16.9991 times 0.0004 plus 17.9992 times 0.0020. Kind of ran out of room there. All right, and then like I did on the previous one, I'm going to type it in exactly as I have here. I'm going to do that off camera, and then I will show you what it looks like in just a second. So 15.9949 times 0.9976 plus 16.9991 times 0.0004 plus 17.9992 times 0.0020. All right. And that comes out to 15.99931.028. Okay. And when I look at that to 2 decimal places, 1, 2, that 9's going to round, 16.00 would be our average atomic mass. Okay. All right, for our third example, potassium has 3 isotopes. The notation here is a little bit different. It's very similar to what we saw in the Zappin chart. Remember, in your chemical formulas for your Zappin charts, it's A over Z with the symbol. So all of these have the same Z, 19, 19, 19, which we should because potassium has 19 protons, and then 3 different A's because these are 3 different isotopes. So we have potassium 39, potassium 40, and potassium 41. I have 2 of my 3 abundances. And so in order to go forth and calculate this, the first thing we have to do is to find our missing abundance. So just like I did in the previous question, I'm going to take 100% and subtract the 2 that I have. 93.26 minus 0.013. And that's going to give me a percentage for my potassium 41 of 6.727%. Okay. I'm going to move my decimal 2 places to the left for each of these. Backfill a 0 on that one. Backfill a 0 on that one. And then I'm going to go ahead and plug in and solve for my average atomic mass. So my mass for the first one, 39 times 0.9326, plus my mass for the second one, 40 times 0.00013, plus 41 times 0.06727. Okay. Adding those up, 39 times 0.9326 plus 40 times 0.00013 plus 41 times 0.06727. 39.1367. And to 2 decimal places, that would be 39.13 is our average atomic mass. All right, for this last example, we're actually going to be working backwards. So, I forgot to write down a number. So let me write down the last number that we're missing. The average atomic mass is 28.083. Okay, now we can go. I have 3 isotopes of silicone, and what I'm trying to find is the actual mass of one of my isotopes, silicone 28. I have the actual masses of the other 2, silicone 29 and silicone 30, as well as all of my abundances. So I would need to go backwards and find my missing one. So think about what we did up here. I took the part times the percent and added them together. This time I need to take the whole and subtract away what I know to help me find the one that I am missing. So it's literally just working backwards. All right, so let's set that up. I'm going to do the same thing I did previously and move my decimal 2 places on all of these before I start. 28.083 minus, okay, I can't do anything with the silicone 28. I'm going to come down here to the silicone 29. 28.9765 times its percent, 0.047, minus 29.9738 times its percent, 0.0319. And once I subtract all of that away, what I'm left with is the silicone 28 times its percent, 0.922. So I'm going to solve all of this off, set it equal to this. And if you think about the silicone 28 as x, I'm essentially just going to be solving for x. So on my calculator, I'm going to do this off camera and then I'll move it up here because of the glare. 28.083 minus, parentheses, 28.9765 times 0.047 minus 29.9738 times 0.0319. And that gives me, oh, hold on, Miss Stein typed something in wrong. Give me just a second. 28.083 minus 28.9765 times 0.047 minus 29.9738 times Oh, that's not a 9. That was the percent sign. I just couldn't read my own writing. Times 0.031. There we go. 25.791967. Oh, and in the glare. There we go. So this is equal to the 28 silicone times its percent. And when I divide by the percent, I'm going to get the 28 silicone. Divide by 0.922. 27.97387928, and to 2 decimal places, 27.97. That is my missing value, 27.97. Okay, hopefully that's helpful.